Hello everyone, I am Mrs. K. Vanitha, working as an assistant professor in the Department of ECE at K.S. Rangasamy College of Technology. In this lecture, we are going to see about IGBT under the module Power Devices and Converters in the course Electronic Devices. So, IGBT is nothing but insulated gate bipolar transistor. We know that BJT and MOSFET are most widely used types of transistors where each of it has its own advantage over other and has some limitations. IGBT takes the best part of the BJT as well as MOSFET into a single transistor. It takes the input characteristics of MOSFET and output characteristics of BJT. So in this lecture we are going to see about its simple construction, working and applications of IGBT. So these are all the things which is available in the market as IGBT. This is the symbol of IGBT, which is having three terminals: gate, collector and emitter. At the output side we are having collector and emitter. At the input side we are having gate, and which is also seen with the symbol of this round. What is IGBT? So IGBT is nothing but insulated gate bipolar transistor. It is the combination of BJT as well as MOSFET. It's a fusion of these two. By the name itself, we can know that insulated gate refers to the input part of MOSFET having very high input impedance. It does not draw the input current. So rather it operates on the voltage at its gate terminal. Bipolar refers to the output part of the BJT. So it allows the current to flow through by both types of charge carriers, nothing but electrons and holes. It can handle very high, very large currents as well as voltages using small voltage signals at the input side, nothing but gate. The hybrid combination makes the IGBT as the voltage control device. So we know, we have seen already the symbol of this IGBT. It's a 4-layer PNPN device, has 3 PN junctions. It has 3 terminals: gate, collector and emitter. The input part is taken from MOSFET, nothing but gate, emitter and output collector are the outputs of BJT. Emitter is directly attached to the P and N regions, but the gate terminal is insulated by means of silicon dioxide. This P plus substrate will inject holes into the N region, so that it is called as injection layer, and this N layer is nothing but drift region, so the drifting of charge carrier will occur, and there will be a channel between this N plus region and the drift region. So by applying this gate voltage, there will be a drifting of charge carriers, movement of charge carrier, which will form or accumulate in the channel, so that the movement of charge carrier will increase the current flow, so that IGBT will turn on. And this P layer is otherwise called as the body of the IGBT, which is further explained over here. Equivalent circuit or equivalent structure of IGBT is given by the combination of BJT at the output side and the MOSFET at the input side, with the gate input terminal and the collector and emitter output terminal. And the resistance of the drift region is given by the resistor. Working of IGBT. Two terminals of IGBT are IGBT. Terminals of IGBT collector and emitter are used for the conduction of current, while the gate is used to control the current flow. So biasing is applied between gate and emitter terminal as well as collector and emitter terminal. So initially when gate is at 0 volt and the voltage is applied between the collector and emitter, and the collector is positive with respect to the emitter, so that this PN junction will be in the forward bias junction. J1 is at the forward bias condition. J2 will be at the reverse bias condition. There is no current flow through the drift region. So so that IGBT is in the off condition. When VGS is increased upon above the threshold voltage, so there will be of movement of charge carrier from, that is, holes from P region to N region, and also this N plus region. So which will form a layer between, which will form a contact between N layer as well as the N plus layer. So the drifting of charge carriers, that is electrons, into the drift layer, that is N layer from N plus region. So movement of charge carrier, that is holes from P plus layer, that is holes to from P plus substrate to N layer, as well as the electrons from N plus layer to the N drift layer. The moment of charge carrier will be increasing, so that when VGS is increased, so that is VG, that is gate voltage with respect to emitter is increased, the moment of charge carrier will be increasing, so that current flow will be increased, so IGBT will turn on. This will be applied the switching circuit or power control devices. So which is further explained over here. The collector emitter terminal is connected to VCC. So collector is kept at a positive voltage than emitter. J1 is forward biased, J2 is reverse biased. There is no voltage due to no voltage at the gate, and due to the reverse bias J2, IGBT remains switched off, no current flow between collector and emitter. When VG is positive than emitter, negative charge carriers will accumulate between that is under the SiO2 layer. When increasing VG, the number of charge carriers eventually form a layer when the VG exceeds the threshold voltage in the upper P region. This form the N channel that shunts the drift N drift region and N plus region. The electrons from the emitter flow from N plus region into N drift region, while holes from collector are injected into the from P region into N drift region. Due to the excess of this both the electrons and holes in the drift region, its conductivity increase. It starts to correct conduction of current, so that IGBT turns on. Next, the applications of IGBT as numerous applications. It is used in AC as well as DC circuits. It is used in switch mode power supply to supply power to the sensitive medical equipment and computers. It is used in UPS. It is used in AC and DC motor drives offering speed control. It is used in chopper and inverters. It is used in solar inverters.